Let's discuss Newton's third law, the law that even Isaac Newton had some difficulties with. Please be patient with yourself if you find that you have your own difficulties with this law. Here's Nellie Newton stating Newton's third law.
Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
We call this the law of action and reaction. I go further and state it's the law that says you can't touch without being touched. Here's a photo of me and my wife Lillian. Am I touching Lillian, or is Lillian touching me? We're touching each other. You can't touch without being touched. To understand Newton's third law, there are two things you've got to do. Number one, distinguish between a force on an object and a force exerted by an object. Number two, identify the system involved. Let's illustrate these ideas, highlighting systems and distinguishing between apples and oranges with Miss Orange and Mr. Apple. Consider Miss Orange sitting peacefully in her cart. The dashed line surrounding Miss Orange encloses and defines a system, the orange system. She sits at rest. That's until a force acts on her. The vector that pokes outside the dashed line represents an external force on the system. The system will tend to move and accelerate toward the right in accord with Newton's second law. Here we see that the force is provided by Mr. Apple, who is outside the system. In third law fashion, we note that the apple can't pull on the orange without the orange pulling on the apple. We show the pull on the apple with this equal and opposite vector. At this point, the pull on the apple is immaterial. It's external to Miss Orange's system. But since the pulls are equal and opposite, don't they cancel? Not so long as they're in different systems. You can't cancel a force on the orange system with an outside reaction force on the apple system. So cancellation of forces does not occur. Now let's consider a larger system enclosing both the orange and the apple. Notice now that the pair of vectors are internal to this system. In this case, they do cancel each other, so they play no role in moving or accelerating the system. That's why I'm erasing them. In a similar way, all the zillions of forces between atoms inside a baseball do nothing to move the baseball. Only an external force on the baseball can move it. To set the system in motion, an external force is needed. That's where friction with the floor plays a role. When the apple pushes on the floor simultaneously pushes on the apple. I'm drawing this dashed vector as the push on the floor. I'm drawing this equal and opposite solid vector as the floor pushing back on the apple's feet. This is the external force that acts on the system. Since the dashed vector doesn't act on the system, I'm erasing it. See all this? Sure, the apple exerts a force on the floor. We don't care about the floor. That's why we erased it. It's outside the system. What we care about is the reaction force by the floor on the apple's feet. It's this force that provides the external force on the orange apple system. In short, apple pushes on floor, floor pushes on apple. Yum. Going a bit deeper, we can consider friction elsewhere, say the cartwheels. If floor friction on the apple's feet is greater than cartwheel friction, the cart will accelerate to the right. When friction forces balance, the cart continues moving to the right at constant velocity. So we see that forces always come in pairs. The force exerted on one object always comes from interaction with another object. You push on a wall and the wall pushes on you. In fact, you can't push on a wall unless the wall pushes back on you. One force can't exist without the other. Suppose for some reason you lose your temper and you hit the wall. Ouch! But you know what? You can truthfully say that the wall hit you. Consider this boxer hitting a punching bag. He can exert 1,000 pounds on a heavy bag. That's some 4,500 newtons. But if he throws the same punch at a piece of tissue paper in midair, he can't hit it even with 1 pound. Why? Because the tissue paper isn't capable of hitting back with 1 pound. Here we see Sammy Strongman being pulled by 2 ropes, one tied to a tree and the other to a horse. Sammy is okay with the tensions in the ropes. He's a strong guy. How would the tension in the ropes compare if the tree were replaced by a horse as strong as the horse on the right? If Sammy keeps his eyes shut, will he be able to tell the difference? Can you see that the opposite pulls on Sammy would be the same? Yes, that's right. The horse on the left would pull on Sammy just as hard as the tree did. Remember, you can't pull on a tree unless the tree pulls back on you. Yum? Now I leave you with this question. Suppose 2 horses pull to the right while the left rope remains tied to the tree. How would the tension in each rope compare with the tension before? Think about that. Until next time, good energy.